Okay, now we're getting into one of my favorite topics in mathematics, and that's differential equations. Let's recap some derivative notation. If we have a function f of x, we'll often note the derivative of the function f with a prime, so f prime of x. It's usually another function of x, let's say g of x. That's one way of noting the derivative of a function. The other way is in differential form, and that's written as df on dx. So traditionally, you know that df dx is the derivative of the function f. And you would have treated this notation as just a symbol, or perhaps just one entity. But what's more useful for us is that df dx, or df on dx, is also the quotient of two differentials. So it's the quotient of two differentials, which also happens to equal the derivative of the function f. So if I demonstrate this by drawing a sample function, if we take 2 points on the function, the difference in height is delta f, and the difference along the horizontal is delta x, and provided that the distances delta f and delta x are small, it is approximately equal to the derivative of the function f. And if we take the limit as delta f approaches 0 and call this the differential of f, df, and also take the limit as delta x approaches 0 and call it the differential of x, or dx, then we can say pretty confidently that df on dx is equal to the derivative of f. So in this scenario, we can treat df on dx as two separate entities, and that means we can separate them, and we can write then the differential of f, df, is equal to the derivative of f multiplied by the differential of x, dx. This is much more useful when we come to solving differential equations. Okay, on to the topic. So what are differential equations? Well, a differential equation is simply an equation that has a derivative or a combination of derivatives of a function, and it's normally our goal to solve the unknown function. And the great thing about differential equations is that it is one of the most useful tools that we have in mathematics. And you'll see it everywhere in engineering, in biology, in physics. They're literally everywhere. Sometimes differential equations can be very complicated, and we may not necessarily be able to find an analytical solution to them. And that essentially means that a solution that we've been able to work out on paper, sometimes we have to use numerical methods to approximate the function f rather than solve it. But let's start with a very simple differential equation, and the most simple form of differential equation is f prime of x is equal to another function of x, let's say g of x. So essentially we have to find the primitive function. Okay, so this is perfectly a legitimate differential equation. We have a derivative of the function f that we have to find. It's an unknown function, and we have a function g of x. Let's make g of x equal to a polynomial. Let's say 3x squared plus 4x plus 1. Alright, so f prime is equal to 3x squared plus 4x plus 1. We can write f prime as df on dx. And remember what I said about separating the differentials. We can rearrange this equation to df is equal to 3x squared plus 4x plus 1 by dx. So to solve for the function f, we simply integrate both sides. So in this case, we've separated the variables. We've got all the f's on one side and all of the x's on the other side. So the solution is then f, which is a function of x, so the d and the integral have the effect of cancelling each other out, If we integrate each of the terms, we get x cubed plus 2x squared plus x, and then importantly, to get the general solution, we must include the integration constant c. So this is what we call the general solution. And the reason why it's called the general solution is because this differential equation pretty much has an infinite number of solutions, because this c here can literally be anything. Okay, it can be anything but another function of x. So it can be a function of, say, q. It can be another function of a different variable, or it can be any number. Okay, let's have a look at another example. And this is where you can see differential equations being applied. Let's have a look at a very basic kinematic equation of acceleration. Okay, let's say that we have an object that has a constant acceleration of a. So it's accelerating towards the right at a constant rate of a. And you may have learned from basic physics that acceleration is the rate of change of velocity, and we can note that as dv on dt. So then separating the quotient, here we have the derivative of the velocity, and now we can solve for the velocity at any given time. So integrating both sides, we can find the general solution for the velocity to be a, the constant rate of acceleration by time, plus another constant. So the velocity is a function of time. Now let's say that the velocity at time equals 0 is equal to u, a starting velocity. So then according to our equation for velocity, we have v at time equals 0, which equals the acceleration times 0, plus the constant c is equal to u. And that means that our integration constant c is equal to the initial velocity, u, and thus the unique solution, v of t, equals the acceleration by time plus u, the initial velocity. But let's extend this further. So the velocity, you may also have learned from physics, is the rate of change of displacement. And we would note this as ds on dt, the derivative of displacement, is equal to the velocity, which we have solved to be equal to at plus u. So we can separate again to find an expression for the displacement. Integrating both sides, we get the general solution of the displacement as a function of time is equal to a half at squared plus ut by the time plus another constant of integration. Let's use k. Okay, so we had an initial value for the velocity at time equals 0 of u, and let's say the displacement at time equals 0, so s of 0 is equal to 0. So we're starting from the point 0. So this is the initial value for displacement, and if I sketch that on a line, let's say this is the point 0, and the object is accelerating away from the point 0 with an initial velocity of u. So we found the general solution for the displacement, but because we have the initial value, we can find the general solution, the particular solution for displacement. And this must mean that the variable k is equal to 0, because we've got rid of the first term by multiplication with 0, the second term by multiplication with 0, and we're left with k is equal to 0. So the particular solution for displacement then, s at any time is equal to half at squared plus ut. We have the velocity at any given time equal to a by t plus u. And if these equations look familiar from physics, that's because this is how they were derived. So that will do it for our introductory video on differential equations. I hope you found this helpful. Please give me a thumbs up, subscribe for future videos that may help you with your studies. I'd appreciate any small tip or donation, and the ways you can help me are in the description below. Thank you in advance. If you have any questions, please comment below. Thanks for watching, and I will see you on the next video.